If you pay attention to what you're feeling right now, not what you think you should feel, but what is actually happening in your hands, your back, the surface you're resting on, it all seems straightforward, almost too obvious to question. The chair holds you. The floor supports the chair. Your body presses down and something pushes back. It feels direct, immediate, solid. That's the word you would probably use without hesitation. Solid. But that word hides something important, because the sensation you're relying on is not coming from matter being packed tightly together the way your intuition suggests. It comes from something far less intuitive, something that only becomes clear when you stop trusting the feeling and start asking what's physically there. Take any object around you. It doesn't matter what it is. Your phone, the table, your own hand, and imagine shrinking yourself down to the scale where atoms are no longer an idea but a visible structure. What you would expect to find is something compact, something filled in, something continuous. What you actually find is very different. Each atom is mostly empty space, not metaphorically empty, but literally empty in the sense that almost all of its volume contains no solid material at all. A useful way to picture it, and I like this because it forces you to confront the scale rather than avoid it, is to imagine expanding a single atom until it fills the volume of a large stadium. The outer boundary of the atom stretches all the way to the seats, to the edges of that enormous space, and somewhere near the center, almost lost in the scale of it, sits the nucleus, a dense cluster of protons and neutrons about the size of a marble. Everything else, the entire interior of the stadium, is occupied by electrons, but not as little particles orbiting like planets in neat paths. They exist as a diffuse cloud, a probability distribution spread out over that vast region. The part that tends to get overlooked is what that implies. If the nucleus holds almost all the mass and the electrons define almost all the volume, then the size of an atom is not determined by something physically solid filling it. But by the way those electrons are arranged, the structure, the space you associate with matter, comes from the rules governing how electrons can exist, how close they can be pushed, how they respond to one another. So when your hand rests on a table, the atoms in your hand are not colliding with atoms in the table like rigid objects hitting each other. Instead, the electron clouds of those atoms begin to interact. As they are pushed closer, electromagnetic forces between them increase rapidly, creating a resistance that prevents them from occupying the same region of space. That resistance is what your nervous system interprets as solidity, not contact in the classical sense, not surfaces touching, but fields interacting. I remember the first time I stopped repeating that explanation and actually tried to follow it all the way through. And it led to an uncomfortable conclusion, because it meant that nothing I had ever touched was solid in the way I instinctively believed. The surface, I felt, was not a surface at all, just a boundary where forces became strong enough to push back. There's a tendency to treat that as a curiosity and move on. But it's more than that, because it tells you something fundamental about matter. The space inside atoms is not an accident, but it's also not guaranteed. It exists because of a balance between forces and quantum rules that keep electrons in those extended configurations, change the conditions, push hard enough, and there is no reason that structure has to survive. And that's the part worth holding on to. Not the image of the stadium or the marble, but the idea that what gives matter its size, its apparent solidity, is something that can, in principle, be removed. A star is easy to misunderstand because from where you are, it looks still. You see a point of light in the sky, steady enough that people have used it for navigation, poetry, calendars, and superstition. And the eye naturally turns steadiness into peace. But a star is not peaceful. It is a machine under stress. And its apparent calm comes from a balance so precise that you only notice it when the balance begins to fail. Inside a star, gravity is always trying to pull every layer inward. It is not dramatic about it. It has no special moment where it begins. It is simply there, acting on every kilogram of gas, every particle, every piece of plasma, trying to compress the star toward its center. If nothing opposed it, the star would not remain a star for long. It would collapse under its own weight. The reason it does not collapse, at least during most of its life, is that the core is producing energy through nuclear fusion. And that energy creates pressure pushing outward. That outward pressure is not a decorative detail. It is what keeps the star alive in the core. Where temperature and pressure are high enough, hydrogen nuclei are forced close together until they can fuse into helium. The process releases energy because a small amount of mass becomes radiation in motion, and that energy works its way outward through the star, pressing against the weight of all the layers above it. Gravity squeezes inward, fusion pushes outward. A star is the temporary result of that disagreement. What I like about this picture is that it removes the romance without removing the wonder. The star is not just burning like a campfire. A campfire burns because chemical bonds rearrange. A star shines because atomic nuclei themselves are being forced into new arrangements under conditions so extreme that ordinary matter would be unrecognizable there. When you look at starlight, you are seeing the visible trace of a pressure system deep inside a gravitational object that would destroy itself if that pressure stopped for a long part of its life. The balance is self-correcting. If gravity compresses the core slightly, the temperature rises. Fusion becomes more intense, and the extra outward pressure pushes back. If the core expands too much, the temperature drops. Fusion slows, and gravity pulls it inward again. It is not a rigid balance like a statue standing still. It is more like a person constantly shifting their weight to stay upright, except the person is made of plasma, and the balancing act can last millions or billions of years. But fuel changes everything. Hydrogen is not unlimited. In a star like the Sun, hydrogen fusion can continue for billions of years. And when the central hydrogen runs low, the star enters later stages that eventually lead to a white dwarf. But massive stars live differently. They burn hotter, faster, and more wastefully. Their cores are more compressed, their fusion rates are higher, and their lives are shorter, not just a little shorter, but enormously shorter compared with smaller stars. In a massive star, once hydrogen in the core is used up, gravity compresses the core further and raises the temperature until helium can fuse into carbon and oxygen. When helium becomes insufficient, the same pattern repeats. Carbon burns, then neon, then oxygen, then silicon. Each new stage demands a higher temperature, and each stage lasts for less time than the one before. The star is not calmly aging. It is being forced into more difficult solutions. This is the part I would want you to notice carefully. The time scale collapses. A stage that once lasted millions of years gives way to one that lasts hundreds of thousands, then hundreds, then perhaps a year, and finally the last major burning stage can last only about a day. From the outside, the star may still appear intact, still luminous, still recognizable. Inside, the sequence has become urgent. The core is building heavier and heavier elements. Not because it has a plan, But because gravity keeps squeezing and fusion keeps finding temporary ways to answer, then the process reaches iron. Iron is not just another step in the chain. It is where the arrangement stops being profitable. Fuse lighter elements, and you can release energy. Try to fuse iron, and you must spend energy. That means iron cannot support the star the way hydrogen, helium, carbon, or silicon did. It collects in the core as a kind of final product, dense and heavy, but useless as fuel for outward pressure. At this point, the star has not exploded yet. That is important. There is still a star there. There is still structure, still mass, still heat, still layers wrapped around the core. But the engine that made the long balance possible has reached a material it cannot use. The core has arrived at a state where producing more pressure through fusion is no longer available. The star is still shining, but its central support has become temporary in the most literal sense. Iron does not announce itself as a problem. It simply accumulates in the core, layer by layer. As the star finishes the last sequence of fusion reactions that once kept everything in balance, from the outside, nothing dramatic has happened yet. The star still shines. It still has structure, but at the center, something has changed in a way that cannot be reversed, because the material that now fills the core no longer provides the pressure needed to resist gravity. Up to this point, every stage of fusion worked in the star's favor. Hydrogen to helium, helium to carbon, carbon to heavier elements. Each transformation released energy that pushed outward against the star's own weight. Iron breaks that pattern. Fusing iron requires energy instead of producing it, which means the core has effectively run out of usable fuel without disappearing. It is still there, still massive, still under immense pressure, but no longer able to generate the outward force that held everything up. Once that happens, the balance doesn't gradually drift away. It fails. Gravity has been present the entire time, waiting without urgency. And now there is nothing left to counter it at the center. The core begins to collapse inward, not slowly, not in stages, but as a continuous fall that accelerates as it proceeds. The size of the core shrinks rapidly, and the density rises at a rate that leaves no time for adjustment. What makes this collapse different from anything familiar is not just the speed, but the conditions it creates. As the core contracts, the electrons that once occupied wide regions around atomic nuclei are forced into a smaller and smaller volume. Their energies increase because quantum mechanics does not allow them to all settle into the same low energy states. They are compressed into higher and higher configurations, packed together more tightly than they were ever meant to be under ordinary conditions. Eventually, the situation reaches a point where electrons can no longer remain separate from the protons in the nuclei. The energy becomes sufficient for a different kind of process to occur. An electron combines with a proton, and together they form a neutron and a neutrino. This is not a rearrangement of atoms. It is a change in the identity of the particles themselves. Two familiar components of matter cease to exist as they were and are replaced by something else. This transformation does not happen in isolation. It spreads through the collapsing core as conditions become more extreme. Each time an electron is captured, there is one less electron contributing to the pressure that resists compression. That reduction allows gravity to compress the core further, which increases the energy of the remaining electrons, leading to more captures. The process reinforces itself. The composition of the core shifts rapidly toward neutrons. At the same time, neutrinos are produced in enormous numbers and carry energy away from the core. They interact so weakly with matter that most of them escape even from this dense environment, removing energy that might otherwise have slowed the collapse. For a brief interval, the energy released in these particles exceeds what the star emitted in light over most of its lifetime. But it is carried away almost invisibly. The collapse continues until the density becomes high enough that a different kind of resistance appears. Neutrons, like electrons, are subject to quantum rules that prevent them from occupying identical states. As they are forced closer together, they begin to generate a pressure of their own, one that does not depend on heat or fusion, but on the fundamental structure of matter. When this resistance becomes strong enough, the inner core's collapse slows and effectively stops. The outer layers of the core, however, are still falling inward at high speed. When they encounter the now stiff inner region, they do not settle gently. They strike it. The sudden deceleration creates a shock wave that moves outward through the star. Energy from the neutrinos helps sustain that shock as it travels through the overlying layers, and the star is torn apart in a supernova explosion. The outer material is expelled into space, carrying with it elements formed during the star's life and during the explosion itself. What remains at the center is the collapsed core, now composed predominantly of neutrons, compressed into a much smaller volume than before. The structure that emerges from this process is not a scaled-down version of the original star. It reflects the conditions that produced it. The electrons that once defined atomic size are largely gone from their previous roles. The distinction between separate atoms has been erased. The matter that remains has been reorganized into a state where neutrons dominate, held together under pressures that no longer involve fusion as a supporting mechanism. A neutron star is the result of that transition. It exists because the previous form of matter could not sustain itself under the conditions imposed by gravity, and a new form of matter took its place. What remains after the explosion is easy to describe in numbers and very difficult to picture in any meaningful way, because the object left behind does not resemble anything in your everyday experience. Not in size, not in density, not in how it interacts with its surroundings. A neutron star typically contains more mass than the sun, sometimes 1.5 or even twice as much. But that entire mass is confined within a sphere only about 20 kilometers across. That is not a comparison meant to impress you. It is a statement about scale that your intuition will resist if you take that seriously for a moment. You start to notice the consequences. The density is so high that ordinary units begin to lose their usefulness. A small amount of material, something you could hold in your hand if it were possible, would weigh millions or hundreds of millions of tons under Earth conditions. This is not because the material has been made heavier in some mysterious way, but because the empty space that normally exists inside atoms has been largely removed. What remains is matter compressed close to the densities found inside atomic nuclei. The gravitational field at the surface reflects that compression. Gravity does not just increase slightly. It becomes extreme in a way that changes how motion works near the surface. If you were to drop an object, it would accelerate far more rapidly than anything on Earth. In fact, anything approaching the surface from a distance would reach speeds that are a significant fraction of the speed of light before impact. There is no gentle landing in such a field. Motion becomes dominated by gravity in a way that leaves very little room for anything else. This has consequences for how the object interacts with its surroundings. Material falling onto a neutron star does not simply accumulate. It releases enormous amounts of energy when it strikes the surface, often in the form of high-energy radiation, such as X-rays. This is one of the ways neutron stars are detected. They are too small to resolve directly with most telescopes. But the energy released by infalling matter can be observed across large distances, the escape velocity at the surface is also very high. To leave the gravitational pull of a neutron star, an object must be accelerated to a speed that is a significant fraction of the speed of light. This means that once matter is near the surface, it is effectively trapped unless it gains an extraordinary amount of energy. The star does not need an atmosphere in the ordinary sense to retain material. Gravity alone is sufficient. Magnetic fields add another layer of complexity. Neutron stars often possess magnetic fields that are far stronger than those found on Earth, or even in ordinary stars. These fields can influence the motion of charged particles near the surface and in the surrounding space, shaping how radiation is emitted and how matter behaves in the vicinity. In some cases, the magnetic field is strong enough to affect the structure of atoms themselves, altering the way they would normally exist. Rotation is equally important. When the core of the original star collapsed, it did not lose its angular momentum. Instead, as its size decreased, its rotation rate increased, much like an ice skater spinning faster by pulling their arms inward. The result is that many neutron stars rotate rapidly, completing multiple rotations each second. Some rotate even faster, with periods measured in milliseconds. This rotation, combined with the strong magnetic field, leads to observable phenomena. In certain cases, beams of radiation are emitted along the magnetic poles, and as the star rotates, those beams sweep through space. If one of those beams crosses your line of sight, you observe regular pulses of radiation. These objects are known as pulsars, and their timing can be extraordinarily precise, providing a way to study the properties of neutron stars in detail. What matters here is not any single number or property, but the combination: high density, strong gravity, intense magnetic fields, rapide rotation. Each of these could exist in other contexts, but not usually all at once, and not usually at these magnitudes. The neutron star represents a point where several physical extremes coincide in a single object. Despite all of this, it is still not a black hole. There is a surface, even if that surface is unlike anything you would recognize. There is still structure, still matter, arranged in a way that resists complete collapse. Gravity has pushed as far as it can without entirely overwhelming the forces that oppose it. The star exists at that boundary. The description up to this point treats the neutron star as a whole, as an object with global properties. That is useful, but it does not tell you what the matter inside actually looks like. Knowing the mass and radius does not explain how the material is arranged beneath the surface or how it changes with depth. To understand that, you have to move inward and consider how matter behaves under progressively increasing pressure, starting from the outer layers and working down. If you begin at the surface of a neutron star and move inward, what you encounter is not an immediate jump into something completely alien, but a gradual breakdown of structures you would still recognize at first. And that's important because it shows you that the transformation of matter is not a single event, but a sequence of changes, each one forced by increasing pressure. The outermost layer is extremely thin, almost negligible compared to the size of the star. And although it is subjected to intense gravity and temperature, it still resembles ordinary matter in a limited sense. You can still speak about atoms there, though they are highly distorted and exist under conditions that would be impossible anywhere else. But this familiarity does not last as you move deeper, even by a small distance. The pressure rises rapidly, and the first thing that disappears is the electron structure that defined the size of atoms in the first place. Electrons are stripped away from nuclei, not because they vanish, but because they can no longer remain bound in their usual configurations, instead of orbiting individual nuclei in well-defined quantum states, they form a dense collective background, often described as a degenerate electron gas. At this point, atoms as distinct entities have already ceased to exist. What remains are bare nuclei arranged in a regular lattice, surrounded by this sea of electrons that moves through the structure. This arrangement is stable under the conditions present in the outer crust, but it is already far removed from anything you would encounter on Earth. The nuclei themselves are no longer the familiar versions of elements, you know. Under increasing pressure, processes occur that convert protons into neutrons within those nuclei, making them increasingly neutron-rich. You are no longer dealing with stable isotopes in the usual sense. These are configurations that exist only because the surrounding pressure prevents them from breaking apart. As you continue inward, the density increases further, and the nuclei are forced closer together. At some point, they reach a limit in how many neutrons they can contain while remaining intact. When that limit is exceeded, neutrons begin to escape from the nuclei. They are no longer confined within a specific atomic structure. They move freely between the remaining nuclei, forming a new component of the matter in this region. This transition is known as neutron drift, and it marks a clear change in the character of the material. Above this point, neutrons are bound within nuclei. Below it, they exist both inside nuclei and as a free population moving through the structure. The matter now consists of three components: neutron-rich nuclei, a sea of electrons, and a growing number of free neutrons occupying the spaces between them. As the depth increases, the fraction of free neutrons rises. The nuclei become larger and more neutron-rich, but at the same time, they are losing neutrons to the surrounding environment. The distinction between what belongs to a nucleus and what belongs to the surrounding medium becomes less clear. The structure is still there, but it is becoming unstable in a very specific way. Not collapsing outright, but gradually losing its identity. Eventually, the pressure becomes high enough that the nuclei can no longer exist as separate objects. They begin to merge, and the lattice structure that defined the crust breaks down. The boundaries between individual nuclei disappear, and what remains is a continuous form of nuclear matter. At this stage, it no longer makes sense to speak about individual atoms or even individual nuclei. The material has transitioned into something that is better described as a fluid of nucleons, primarily neutrons, with a smaller number of protons and electrons still present to maintain charge balance. This is the point where the concept of atomic structure fully ends. There are no electron shells, no chemical bonds, no discrete elements in the sense you understand them. The properties that depend on those features, hardness, elasticity, chemical reactivity, no longer apply in any meaningful way. The behavior of matter is now governed by nuclear interactions and quantum mechanical effects at densities far beyond those accessible in any laboratory. What makes this progression significant is not just the final state, but the path taken to reach it. At each stage, familiar structures are altered rather than abruptly replaced. Atoms lose electrons. Nuclei gain neutrons. Neutrons begin to move freely. Nuclei merge into a continuous medium. Each step follows from the conditions imposed by gravity and pressure. And each step removes another layer of the structure you associate with ordinary matter. By the time you reach the base of the crust, the transformation is complete in a practical sense. The material no longer retains any recognizable features of atomic matter. What exists instead is a dense, continuous system where the distinctions that once defined matter at smaller scales have been eliminated. Between the last recognizable remnants of nuclei and the fully uniform core, there is a region where matter does something unexpected. Not because new particles suddenly appear, but because familiar forces begin to compete in a way that produces structures you would not normally associate with nuclear matter. The densities here are high enough that nuclei are no longer isolated, yet not high enough for everything to merge into a continuous fluid. The result is a transition zone where geometry itself becomes part of the physics at slightly lower densities within this region. Nuclear matter still forms roughly spherical clusters, but they are much larger and far more neutron-rich than anything found under normal conditions. As pressure increases, these spheres are forced closer together, and the balance between the attractive nuclear force and the repulsive electromagnetic force changes. It becomes energetically favorable for the spheres to connect, forming elongated structures. The geometry shifts from isolated clusters to extended shapes, and with further compression, those shapes flatten into layers. The sequence is continuous rather than abrupt. Spheres become rods. Rods become sheets. And then the pattern reverses as the roles of dense and less dense regions invert. Instead of dense regions embedded in a background, the background itself begins to form voids within a dense medium. These configurations are collectively referred to as nuclear pasta, not because the name carries any deep meaning, but because it provides a convenient way to describe a set of structures that would otherwise be difficult to visualize. What matters is that these shapes arise from fundamental interactions, not from any external design. The presence of these structures indicates that matter is reorganizing itself to minimize energy under competing constraints. The nuclear force favors compact arrangements, while the electromagnetic force pushes charged components apart. At these densities, neither effect completely dominates, and the compromise between them produces patterns that are stable under the conditions present. The material in this region is neither a conventional solid nor a simple fluid. Its mechanical properties are determined by these extended structures, which are held together by interactions at the level of nucleons. As the density continues to increase, the distinction between structured regions and the surrounding medium fades. The pasta phases give way to a more uniform composition, and the system transitions into what is known as the outer core. Here, the matter is predominantly neutrons, with a smaller fraction of protons and electrons present to maintain charge neutrality. The composition is set by a balance between processes that convert neutrons into protons and electrons, and the reverse processes that convert protons and electrons into neutrons. This balance leads to a stable ratio. Under the prevailing conditions, the behavior of matter in the outer core is governed by quantum mechanics in a way that differs from ordinary materials. Neutrons, being fermions, cannot occupy identical quantum states. As their density increases, they are forced into higher energy configurations, generating a pressure that resists further compression. This neutron degeneracy pressure plays a central role in supporting the star against gravity. Unlike thermal pressure, it does not depend on temperature, but on the quantum properties of the particles themselves. In addition to this, interactions between neutrons through the strong nuclear force become significant. At the densities present, neutrons are close enough to influence each other directly. The combination of degeneracy pressure and strong force interactions determines how the matter responds to further compression. The system behaves as a dense quantum fluid rather than as a collection of independent particles. Under these conditions, another effect emerges. Neutrons can pair up through an interaction that allows them to form correlated states. When a large number of such pairs occupy the same quantum configuration, the system enters a superfluid phase. In this state, the fluid can flow without viscosity, meaning that it does not lose energy through internal friction in the usual way. This is not a speculative idea. It is supported by observations of neutron stars that exhibit sudden changes in their rotation rates, phenomena that are best explained by the presence of a superfluid interior. Protons, although less abundant, can undergo a similar pairing process, leading to superconductivity. In a superconducting state, electrical currents can persist without resistance, and magnetic fields become organized into quantized structures. These effects influence how the star's magnetic field evolves and how it interacts with the rotation of the star. The outer core, therefore, is not just a dense region of matter, it is a system where multiple quantum phenomena coexist: neutron superfluidity, proton superconductivity, and a background of electrons that mediate interactions. These components are coupled in ways that affect the macroscopic behavior of the star, including its rotation and its emission of radiation. By the time this region is reached, the transition from atomic matter to nuclear matter is complete. The structures that dominated the outer layers have been replaced by a continuous medium whose properties are determined by interactions at a more fundamental level. The sequence of changes leading here reflects the progressive adaptation of matter to increasing pressure, with each stage removing features that are no longer sustainable under the conditions imposed deeper inside. The description that worked before begins to lose clarity, not because the matter stops existing in an ordinary sense, but because the way we have been describing it, neutrons interacting in a dense fluid, depends on the assumption that neutrons remain identifiable as individual objects, and at sufficiently high densities, that assumption is no longer guaranteed to hold. A neutron is not a fundamental particle. It is composed of quarks bound together by the strong nuclear force under normal conditions. Those quarks are confined within the neutron, and the neutron behaves as a single unit, but as the density increases in the inner core, the average distance between neutrons decreases to the point where they begin to overlap. When that happens, the internal structure of the neutron can no longer be ignored. The distinction between one neutron and another becomes less meaningful because their constituent quarks are no longer isolated from each other. This leads to the possibility that matter in the inner core undergoes another transition, one that is more difficult to describe than any of the previous ones. Instead of neutrons remaining intact, the quarks inside them may become deconfined, meaning they are no longer bound within individual particles, but can move over larger distances within the material. In this scenario, the matter is better described as a quark fluid, a state in which up and down quarks and the gluons that mediate their interactions form a continuous system. Such a transition would represent a fundamental change in the organization of matter. The building blocks are no longer nucleons, but quarks themselves. However, this is not something that can be confirmed directly through laboratory experiments. The conditions required, high density and relatively low temperature, are not accessible with current technology. The existence of quark matter in neutron star cores remains an open question. Supported by theoretical models, but not definitively established, another possibility arises when considering the role of different types of quarks. In addition to up and down quarks, there exists a slightly heavier type known as the strange quark. Under extreme conditions, it may become energetically favorable for some of the quarks in the system to convert into strange quarks, leading to a form of matter known as strange quark matter. In this state, the material would consist of a mixture of up, down, and strange quarks in proportions determined by energy considerations This idea has significant implications if strange quark matter is more stable than ordinary nuclear matter at these densities. Then the inner core of a neutron star could consist largely of this form in more extreme interpretations. Entire stars could be composed predominantly of strange matter rather than neutrons. Although distinguishing such objects observationally is challenging, there are also intermediate possibilities. Instead of a complete transition to deconfined quark matter, the system might include other composite particles, such as hyperons, which contain strange quarks but remain confined within particle-like structures. The presence of hyperons would alter the equation of state of the material, affecting how pressure relates to density and therefore influencing the overall structure of the star. The difficulty in resolving these possibilities lies in the complexity of the strong force at high density. While the theory describing quark interactions is well established, solving it under these conditions is extremely challenging. Many of the computational methods that work at high temperatures do not apply in the same way at high densities. As a result, different theoretical approaches yield different predictions, and there is no single agreed-upon description of the inner core. Observational data provides some constraints, measurements of neutron star masses, radii, and responses to gravitational interactions can limit the range of possible equations of state. For example, the existence of neutron stars with masses around 2 times that of the Sun suggests that the internal pressure must be sufficiently large to support that weight. This requirement rules out some models while leaving others viable. Gravitational wave observations from neutron star mergers add further information by revealing how the stars deform under tidal forces. These measurements are sensitive to the internal structure and can help distinguish between different models of dense matter. However, even with these advances, the data does not yet uniquely determine the composition of the inner core. What can be said with confidence is that the inner core exists in a regime where matter is pushed beyond the conditions under which it has been directly studied. The transitions that may occur there involve changes at the level of fundamental constituents, not just rearrangements of atoms or nuclei. Whether the matter remains in a form that can still be described in terms of neutrons or transitions into a quark-based state depends on details that are still being investigated. The description of the neutron star has moved from familiar structures at the surface to increasingly abstract ones at greater depths. By the time the inner core is considered, the language required becomes less certain. Reflecting the limits of current knowledge, the progression from atoms to nuclei to neutrons and potentially to quarks illustrates how the organization of matter changes under extreme conditions, with each stage defined by the forces that dominate at that scale